and set up from the current slide. And Mark Thomas kind of here. And let's go over the announcements. 2 weeks from yesterday, on February 12th, the Lawson State College Community College Transfer Fair Day will be held on the Birmingham West Campus in the academic building, which is B Hall, from 9:30 to 11:30. That's Wednesday, February 12th. They'll probably have tables all up and down that long hallway with various universities and colleges at those tables. Then 2 weeks from today, which will be Thursday the 13th of February, we'll have it from 9:30 to 11:30 here in this building. Yes?
When did you say the transfer day was?
On Wednesday the 12th on the Birmingham West Campus, and Thursday the 13th on this campus. And on this campus, it will be in this building, but they say it'll be in the campus cafeteria, which I kind of doubt, because the campus cafeteria is just not that big, and that's going to be the end of breakfast and the beginning of lunch, and I just can't believe they're going to all be fit in there during that. My better guess would be the faculty staff dining room, which is just next to the cafeteria. It's a pretty good sized room, has lots of tables in it already. It may not be big enough for all of them, so a few of them may be in the cafeteria, or a few of them may be in the hall on the other side of the faculty staff dining room. That would be my guess. But go down to that general area, you'll find them 9:30, 11:30, 2 weeks from today. Okay? If you want to see a list of all the schools who have been invited, you're certainly welcome to take a look at them. Worth going to there just to find out the type of questions they asked, the information they've got. It's worth it, even if you're not that close to graduating, which I'm guessing most of you are. And then for those who especially are going into pre-engineering, mechanical, electrical, or material engineering, there is that fantastic research experience coming up at either University of Illinois, University of Arkansas, or Howard University. 10-week internship exposes undergraduate students to academic research, and it's an incredible learning experience. And guess how much you pay? Absolutely nothing. They pay you $5,000 for this great learning experience over 10 weeks, okay? I don't know how they pay it, one lump sum or so much a week or whatever, but anyway, they pay you $5,000 to go. They give you free housing at one of those three universities. Usually the free housing includes a meal ticket, which feeds you for 10 weeks. That's pretty good. And they pay you airfare there and back once. Okay, round trip airfare once. Can't get much better than that. Okay, so if you're interested, they say on the email the application deadline was February 15th, but when I looked in the brochure, I hadn't noticed it before, I saw that it's February 17th. I was suspicious about the 15th because that's a Saturday, and they usually don't have deadlines being on Saturday, and here it says it's Monday. Just get your application in before then, okay, and be safe. All right. I think I've got everybody marked. Hopefully some more will be coming. Any questions on anything we've done up till now? Okay. Where we left off last time, according to my mark here, is in Chapter 4, trigonometry, of course. 4.3 is right triangle trig, and example 6, which they don't have on the PowerPoint. So I've turned back to the example 5, and we'll do example 6 here. It's applying trigonometric identities. Okay, and let me get my pen set up. Okay. Let theta be an acute angle such that tangent theta is equal to 1 over 3. Now, you might bang your head around and try to think, if you do, well, think always, but think about it too hard, you'll say, wait a minute, that's not one of our favorites. That's not one of those that we know just looking at it. Okay? And this is second. Ian. Okay. I was going to guess that, but I was going through my options first. Ian. Okay. We're doing example 6. It's not on the slide set, so we're doing it. Such that tangent theta, we're looking for theta. No. They say let theta be an acute angle such that the tangent of theta is equal to 1/3. Okay? Then what we're looking for is find first the cotangent theta. Okay? And then find the secant theta. Okay. Now, that's all they've given us. Theta is an acute angle, and its tangent is 1/3. Okay? Now, there's a couple ways you could go about doing this problem. Okay? They want you to just use the identities. So that's okay, we can do that. Can you give me cotangent theta just from what they're given here? How? Flip them, because the cotangent is reciprocal of tangent. So that would be 3. Done. That was the easy one. All right. Secant theta. There is a way you can do it from the identity, and it's perfectly okay. Personally, I don't care for it quite so much. Okay? Here's how I would approach this one. Okay? Let's go back to this tangent theta is 1/3. What is tangent theta? Always, tangent is, second? We know it's 1/3, but what is tangent in general defined to be? Okay, it is that, but more basic. What is tangent? Taking oats away. Opposite over adjacent, right? So your opposite side is 1, your adjacent side is 3. Now, I don't know if I've got them drawn well. Probably that's not even close to a right triangle, but let's just pretend it is. That this is 1 and this is 3. Okay? Now, what are we missing? Hypotenuse. Okay. We don't know what it is. Okay? But it's fairly easy to get. Now, what is secant theta in terms of those same sides? What is secant? Hypotenuse over adjacent. Now, that one, it might do, is 1 over cosine. Cosine is adjacent over hypotenuse. Yeah, so it's hypotenuse over adjacent. So we do need to know that hypotenuse. What is it? Is what? How? Okay, Pythagorean theorem. And what does that tell you it is? Square root of 10, is that what I heard? Y'all are good. Okay. How do we get that? We squared this side. 3 squared is 9. 1 squared is 1. 9 and 1 is 10. The square root of 10 is hypotenuse. Right? A squared plus B squared equals H squared. Okay. Or C squared. Okay. And that would be 10, but the H would be square root of 10. Okay. Now, with that in mind, you can just write it down. What is the hypotenuse? Root 10. And the adjacent? 3. There it is. Now, that's not how they wanted you to do it. They wanted you to use the identities. But to me, this is so much easier. Okay? So let's do it by the identities. What identity relates secant and tangent? One of the identities. If you look back one page, page 280, and by the way, I meant to do this earlier, and I forgot. A student who had this class before, I think it's the same book, she left this for anyone who wanted it, okay? It's mostly this course. It looks like it may be missing a few pages. She has a whole bunch of notes in here too, but it's mostly for this course. So there's, like I said, a few pages missing. Does anyone need this? Yours for the ask? You don't have it. Okay, you got it. You can throw out her notes if you want to. You can do anything you want to with it. She left it here. It's been on my desk I don't know how long. Several times this class hasn't made. I almost forgot it was here until I noticed the other day. I said, I think that's trig. And I just opened it. And it's mostly, she's missing a few pages, but that's it. So, what's the relationship between secants and tangents? Anyone remember? Say again? It's one of the Pythagorean identities. Remember, we use the Pythagorean theorem here, so that's a good chance it's going to be a Pythagorean identity. Which one? How does that one go? That's it. 1 plus tangent squared theta is equal to secant squared theta. And we can do that just knowing tangent. So 1 plus, and what's tangent theta? 1/3. So 1/3 squared is 1/9. And that's equal to secant squared theta. Okay? So, what is 1 plus 1? How many ninths is 1? 9 ninths. This will be 9 ninths plus 1/9. Ninth is equal to, that shouldn't be a 19. Okay. Is equal to 10 ninths, and that's equal to secant squared theta. We're really not too interested in what secant squared theta is. We want to know what secant theta is, right? So what do? Take the square root, is that what you said? Okay, now, when you take a square root of both sides, usually you introduce a plus or a minus, right? But this we knew was an acute angle, so we're only going to use the positive square root. Because in the first quadrant, everything's positive, okay? So we're not going to deal with the negative. So if you take the square root of both sides, what do you get? Square root of 10 over, what's the square root of 9? 3. That's equal to secant theta. Ding, ding, ding. Same thing we got there. And this was pretty easy too. I think the other was a little bit easier, but they both work. This is how they wanted you to do it, using the Pythagorean, using your identity, and this one happened to be a Pythagorean identity. Okay? Make sense? But they show you the triangle, and they said you can use that to check your results. In my mind, use the triangle to give you the results is easier. So there it is. There is a checkpoint, and if you can't get that checkpoint, the answers are in the back. I just saw, even in hers, she has the checkpoint answers back there. If you can't get it, you go to Audio Video Solution is at larsonprecalculus.com. All right, neither do they do example 7, so let's us do that one. Any questions on this one before I lose it? Yeah or nay? No question? Oh, I'm sorry, I lost it. Were you still looking? Oh, okay, all right, good deal. All right. Example 7. Use trigonometric identities to transform the left side of the equation into the right side, and what they tell you is 0 is less than theta is less than pi halves. Okay? So in other words, we're in acute angles again, not anything beyond that. So here is the A one. The left-hand side says that sine theta times cosecant theta is equal to 1. It says use the trigonometric identities to transform the left side, sine theta, cosecant theta, into the right side, which is just 1. How are we going to do that? Now, the next section in the text is going to be basically, no, the next chapter in the text is going to be using trig identity. I mean, solving trig identity, all that kind of stuff. This gives you a little flavor of it. This one's a fairly simple one. It may not look like it, but I'm going to give you one of my favorite techniques. They don't like it as much, but it is one of my favorites. Anytime you have something that's you can't see where to go, try changing everything to sines and cosines. Sine is already sine, so don't mess with it. Is cosecant at all related to either a sine or a cosine? Using your trig identity. What is it? Okay, but in terms of sine and cosine, what is cosecant? Okay, not that. Any cosecant is always an identity, one of your trig identities. How is cosecant related to sine or cosine? Second, reciprocal of sine, meaning 1 over sine theta, right? Okay, that's a question mark here. Is it still a question mark here? Well, sine over sine is 1. So this is indeed 1. Question mark goes away. That's it. Right? Now, is that okay? Okay, let's look at B. Oh my goodness. Cosecant theta, they seem to like that one. I can't seem to write either. I think I was writing a theta before I finished writing cosecant. Cosecant theta plus cotangent theta times cosecant theta Aaron? Deal. We're on example 7 on page 281, bottom of 281, section 4.3. Cosecant theta minus cotangent theta. And they say that's equal to 1. So they say use the identities on this side to see if we can make it that side true. Now, what I said before will still work if you change everything on the left-hand side to sines and cosines. It will still work. That won't be the easiest way to do this problem because there's a certain feature of this problem you really need to take note of. What do we call when you have the sum of two numbers, but we also have the difference of the same two quantities? Anyone remember what that's called? And we didn't usually use it in this context, but it's still called this, the conjugate. This is the conjugate of that, that's the conjugate of this. The first ones are the same, the last ones are the same, but the signs are different. Those are conjugates. Okay? Now, when you're multiplying two conjugates, what do you get? Think back to algebra. A plus B times A minus B. Say again? Oh, I thought someone said something. okay, you get the difference of their squares. A squared minus b squared, right? That's what you get. So let's do that to this one and see what happens. This square, you can FOIL it if you want to. It works too. This would be cosecant squared theta. And if you did the inners and the outers, you see that's a plus and that's a minus. And they're the same thing. Those add to 0. Then it's minus cotangent squared theta. It's pretty ugly writing. Equal 1. Okay? It's really ugly writing. Let's see if I can clean that up a little bit. It's just ugly. Okay, I'm not sure I can clean it up too much. Okay, and that's cotangent squared theta. Okay? Now, remember when I did the first one, I said when you can't think of anything else to do, change everything to sines and cosines. Okay? We thought of something else to do. We multiply those two together. Now we got some squares in there. Whenever you see squares, think what kind of identities? What kind of identities always have squares in them? The Pythagorean identities. Okay? Now, does this one look anything like the Pythagorean identity? Ooh, that last one that we had 1 plus cotangent squared theta is equal to cosecant squared theta. Look at that. All we have to do is subtract a cotangent squared theta from both sides. That's legal in most states, right? That goes to 0. You get 1 is equal to cosecant squared theta minus cotangent squared theta. That is a Pythagorean identity. It's absolutely true. Okay? Now, that's not the only way you could do it, but that's sort of to me, the probably easiest. Recognize that as multiplication by a conjugate, and that gives you the multiplying the sum times the difference of the same two entities gives you the difference of their squares. When you write that down, then look at your Pythagorean identities, and that one, just a little manipulation of it gives you exactly that identity. Okay. Now, if you look at the book, they just say that's equal to that, you know, and it is. Yes.
So, bottom part, squared minus cotangent squared.
Yeah.
Could you just,
Huh?
could you just add the cotangent squared to both sides?
Yes, and you get that identity right up there. Yeah, you can do it that way rather than this way. Yeah. Yeah, add cotangent squared to both sides. That gives you the Pythagorean identity. Perfectly fine. Doing the same thing we did. I just subtracted there. You could add down here. Perfect. Good observation. There is a checkpoint at the bottom. Please do the checkpoints as soon as you can after class, and see if you can do a couple more of those. Okay. Any questions before I move on? Everybody got it? Or you need a little longer with it? Okay? So let me go on to the next topic, which is applications involving right triangles. Okay, one pretty good thing about this text is when they do something, they usually give you some application for it. Many applications in trigonometry involve a process called solving right triangles, okay? And you might not know they needed to be solved, but that's what we're going to do. In this type of application, you usually give them one side of a right triangle and one of the angles. You're asked to find one of the other sides. Or you're given two sides and are asked to find one of the acute angles. Okay? Now, when we get to the third chapter that we're going to do today, on this term, not 4, which we're in now, or 5, which is identities, 6, we're going to be doing this even if they're not right triangles. Right now we're going to deal with right triangles. So in example 8, which is coming up next, the angle you're given is the angle of elevation. Okay? So what we mean by that, if I were standing here, okay, I am standing here, but before I stand there, I'm going to mark Nikhil, right? Okay. Nikhil first. Okay, the bottom part of the alphabet is doing outstandingly well today. The top part is completely absent. The first 3 people are not here, but y'all are here. Way to go. Okay. All right. If I were standing here and I was trying to estimate the angle between here and the top of the B building, C building, no, not B, D, E, whatever those buildings are over there, I would, if I had me a nice level and a sextant, I would measure the angle above horizontal to the top of that building. That's called the angle of elevation. If there was a plane up there I was trying to track, that would be its angle of elevation. Now, sort of the reverse of that, if I'm trying to determine the base of that tree down there, I'm up here and I measure the angle from the horizontal downward. That's the angle of depression. Okay? The angle of the elevation is the angle above the horizon, horizontal, and the angle of depression is the angle below. So this one, number 8 is coming up, you're given the angle of elevation, which represents the angle from the horizontal upward toward an object. Angle of depression being from horizon to downward toward the object. Okay. So, here comes example 8. No, it isn't. Okay. Sorry. I thought they weren't going to show this slide, but they did. So, in other applications, you'll be given an angle of depression, which represents the angle from the horizontal downward to the object. Here's your angle of elevation, always measured from horizontal, or angle of depression is measured below the horizontal. Okay. Now, this, depending on which way you look, it doesn't matter. That's usually an acute angle, okay, and it's usually in our regular counterclockwise direction. This one is typically clockwise, but don't make it negative, okay? You're talking about the angle here. You're not worrying about that it may be clockwise rather than counterclockwise. You're just talking about the angle. So don't confuse the issue with the minus sign. Okay. Now we're ready, I think, with example 8. A surveyor is standing 115 feet from the base of the Washington Monument, which is in Washington, D.C., by the way, shown in the figure. Now, 115 feet is not that far away. It sounds far, but it's really not too far away from it. It's shown below. He measures the angle of elevation to the top of that, way up there. Now, that's a tall thing. He's not standing too far away from it. At 78.3 degrees. He has a sextant which measures from the horizontal upward. Okay? 78.3 degrees. How tall is the Washington Monument? Wait a minute, don't I have to climb the Washington Monument and measure it to give that answer? No. Trig takes the work out of it. That's why we like trig, because you can be lazy with trig. You don't have to climb the Washington Monument. Okay? So how are we going to find that? Okay? Here we have an angle, 78.3 degrees. Now we're assuming, if you've ever been to Washington, D.C., you know this is pretty true. It's pretty flat. Okay? It is pretty flat. So if he's 115 feet away from the monument, he's usually horizontal to it. Okay? So, no hill here or anything else. So what he's doing, you're measuring from here. Now we assume also that the Washington Monument is vertical. It's not the Leaning Tower of the Washington Monument or Leaning Tower of Pisa. This is vertical. So this is a right angle here, okay? Monument to the ground is a right angle. Oh, it's on flat level ground. So if this is a 78.3 degree angle here, we know how far he is from the base of the monument, 115 feet. What we're looking for is y. Okay? So, what relates this angle, that side, and this side? What trig function relates them? Tangent function, because this is the opposite side, that's the adjacent side. So you can write down right now that tangent of 78.3 degrees is equal to y over 115 feet. Isn't that true? Okay. Now your y will be measured in feet because we're using 115 feet there, so it will come out to 115 feet. How do you solve that for y? Multiply both sides by 115 feet. I'm going to leave off the feet there because I don't have room. So those go away. So you have y is equal to 115 feet times the tangent of 78.3 degrees. Okay, what? Pull out your calculator. What mode did you better be in? Degree mode. So plug it in, plug it in. Yes.
Is it 9,004.5?
9,000? Is that what you said? 9,004.5. Is that what you said? Okay, my hearing's bad. That sounds a bit large. Okay? Are you in degree mode? Okay. And you typed in 115 times tangent of 78.3. Second? 555 feet. That would be your y is approximately 555 feet. Pretty tall, okay? And by the way, I'm trying to remember, make sure I'm right on this. I believe that's required to be the tallest point in the District of Columbia. I don't think they allow any building to be built taller than that. Even the Capitol building, the dome can't be any taller than that. I think that's the case. You can check your documents to see, but I believe that is the case. So therefore, the Smithsonian Institute, all like this, they only limit it to like 3 or 4 floors or something. Anyways, they can't be any taller than the Washington Monument. I believe that's the case. Okay? Any questions on this? All right, let's see how they did it. From the object, you can see that from the figure, you can see that the tangent of 78.3 is the opposite over adjacent. And you use that because y over x, the y is what you're looking for, the x is the 115 feet. So you do multiply both sides by x, or 115, and you get 115 times, approximately equal to 115 times tangent 78.3 degrees would be about 4.82882. I wouldn't have done it that way, I just done it on the calculator. It's close to 555 feet. Just a little historical note here. I also teach physical science, you know, right? Okay. There was, within the last 6 or 8 years, it seems like, a very minor, but definitely an earthquake, and we don't usually have them here on the East Coast, somewhere in Northern Virginia, I think, somewhere around Virginia. And when it happened, it was minor quake, but it was enough to do a little damage to the Washington Monument. And they had to inspect the monument. They found out it did have some cracks in it. They had to close it down until they reinforced it. And I think it was closed for a year or more. I think it's open again, but you used to be able to climb stairs in the Washington Monument and look from the top. Since it's the highest point in the District of Columbia, you can see everything else in the District of Columbia from that vantage point. But for a year or more, it was closed because they had to do repairs because of that earthquake. So I think it's reopened again. Now, there could be other safety concerns or sniper concerns or things like this that they may be limiting it still, but I don't know. But that has nothing to do with this. But you're way up there. All right. Trying to find where this statement is here. I think this is the top of 283. Yes, it is. Okay. So before we go there, let's do example 9. All right. Here's example 9. Not on the slide sets, so let's do it here. A lighthouse is 200 yards from a bike path along the edge of a lake. Okay? So, here is the lake back here. Okay? And you have a bike path that goes right along the edge of the lake. So here's the bike path. Oops, that's a pretty ugly one. Okay? There's your bike path. There is a lighthouse, and the lighthouse is here. Okay, now I'm not going to draw it, but yeah, that's the lighthouse. Okay, lighthouse. And it's 200 yards from a bike path along the edge of the lake. And when they say that, usually that means shortest distance. So this is 200 yards. Okay? But that's a nice grassy area. They didn't want people walking on that. So for some reason, they put the walkway to be here to get to the lighthouse. I don't know why, but they did. Okay? A walkway to the lighthouse is 400 yards long. From here to there is 400 yards. Okay? Poor planning in my book. It says, find the acute angle theta between the bike path and the walkway. That's what we're looking for, theta. Between the bike path here and the walkway here. Okay? That acute angle between the two. Okay? Now, what trig function appears to be the best one to use to determine that theta based on what we have? Say again? Sine. Because if you're assuming this is your right angle, which we said shortest distance, that would be perpendicular, then this would be the opposite side, and this would be your hypotenuse. So sine. So the sine of your angle theta that you're looking for is equal to opposite over hypotenuse, which in this case is 200 over 400, and they're both in yards. Make sure they're in yards. 200 over 400 yards. Yards cancel out, the zeros cancel out, and this is 1/2. So sine of theta is equal to 1/2. Whoa, that is one of our favorites, isn't it? What is that angle theta? 30 degrees. Okay? So this would be 30 degrees. Or pi 6 radians. Of course, we always think in terms of that, don't we? Nah, 30 degrees. By the way, there are checkpoints after each of these two examples, like there are after every one, and you can please do those as soon as you can after class. And if you can't figure out the answer, and the answers for the checkpoints are in the back of the book. And if you can't get that answer, you can't figure out how to get it, go to larsenprecalculus.com. All right. Any questions? Okay. All right. This is the top of 283. By now, you're able to recognize that theta equals 30 degrees is the acute angle that satisfies the equation sine theta is equal to 1/2. We just did that. We had sine theta equal to 1/2. We know that. That's 30 degrees. Suppose, however, you are given the equation sine theta is equal to 0.6, and we're asked to find the acute angle theta that represents. Okay? Now, they're not asking you to do that yet. We're going to get to that. Okay? They're just saying, give an idea of what that angle is. Well, we know that sine theta, sine of 30, is 1/2, which is 0.5. Okay? Well, that's fairly close to 0.6, but not exact. We also know that sine 45 degrees is 1 over root 2. I don't know if you know what 1 over root 2 is, but it's 0.7077, blah, 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 blah. Okay? So we know that the angle theta here is going to be between 30 and 45 because your 0.6 is between 0.5 and 0.7. Now, it's not a linear relationship, but you can approximate it by that. So you just know it lies somewhere between 30 and 45. If I were making a guess, I would say 38 degrees. Something close to 38 degrees. Now, I shouldn't be doing this yet, but I'm going to show you how you would do this. Okay? Got your calculator. We haven't done this yet. If you see your sine function on it, right? Either just above it or somewhere there's a thing that says sine inverse, right? Sine with a -1. You see that on your calculator? Okay? So, what I want you to do is depends on your calculator. Some calculators you put in the 0.6, then hit that key. Others you do hit that key, the inverse sign, and then press 0.6. See what, be sure you're in degree mode, by the way. What do you get? You may have to do a couple times so it's trying to get it right. Say again? 36.82, that sounds very reasonable. I was guessing 38, 36.82 is close to 37. Good. That's how you find it. Not exactly, but much more precisely than what I did. Okay. Now, they're also skipping example 10. So let's go back and do example 10. Find the height, C, and the base, find the length, I can't read. Find the length C and the base B of the skateboard ramp below. Okay? Here's the skateboard ramp. Here's the ground, and we'll assume that's horizontal, whether mine is or not. And we say this is going to be 13 feet. Okay? Now, we're going to look for base B, or side B, and we're going to look for length C. And we're assuming, and they show in the picture, that is a right angle there. They tell you this angle here is 18.4 degrees. Okay. They're asking for two things, C and B. All right, let's start with C. What relationship, function, calculates this angle, that side, and that side. Cosine. So let's write down what we're saying. Cosine of 18.4 degrees. What's the relationship of cosine in those two sides? 13 divided by c, right? It's not that hard of math to figure that out. What would you do first? Multiply both sides by c, and then that'll wipe out the c's here. Then I would divide by cosine 18.4 degrees. I don't know where to do it. I'll just put it here. Cosine of 18.4 degrees. Okay? That wipes this out. So C would be equal to 13 divided by, oh, be sure you're in what mode? Degree mode. So C would be equal to 13 divided by cosine 18.4 degrees. And what do you get? Anyone want to make a guess? Is it longer or shorter than 13? Anyone want to make a guess? Longer or shorter than 13? That's the only length they gave us here. Is C longer or shorter? Say again? Longer, okay? Why? It's the hypotenuse. Hypotenuse is always longer than the two sides. Not much longer, but how much? Have you already done it? 13 point what? Sorry. Thank you. I want to make sure y'all were awake. Okay, did you say 13.7? Okay, 13.7 feet. Well, now my pen got scared by my sneezing. 13.7 feet. I would round that up to 14, but I guess they left it in the book. They said 13.7. All right. That gave us C. How would we get B? In other words, you're trying to build this, so you want to cut that piece of plywood to be 13.7 feet long. But your brace on the other end, you need to make sure it is good and steady. How long does it need to be? Okay. How would you approach it? Tell me. You have a couple of ways. I think one way is better than the other. How would you approach it? Say again? Oh, very good. The trig function I would use to, I agree with you, is tangent, because the tangent of 18.4 is b over this. Why would you not use that? Because that's a derived quantity, it was estimated. I should have estimated that. You had to round off. Whenever you round off, you introduce some round off error. So use the things that you know precisely. So therefore, I would use tangent. You could use Pythagorean theorem, but again, you're using that. You could use sine, but again, you're using that. Using tangent, you're using the things you were given. So that's how I would do it. And this, what's the relationship there? Tangent of 18.4 degrees is equal to b over 13 feet. And how would you solve that for b? Multiply both sides by 13 feet. And 13 feet cancel out over here, and b is equal to what? And what'd you get? Say again? 4.3? Is that what you said? 4.3 feet. Okay? And that's what they got in the book. Good for them. Okay. Then they have a checkpoint, which is very similar to the one we just did, except now we're looking for A and C rather than B and C. All right, they gave you B, basically. All right, any questions on 4.3? Before we leave it, let's do vocabulary. Now, it says here, match each trigonometric function with its right triangle definition. Okay, in other words, these are our, some old hen called another hen. Yeah, only you use the real word for it. What is your definition of sine? Opposite over hypotenuse, some old hen, that's Roman numeral little 5. Cosine? Adjacent over hypotenuse was Roman numeral little 4. Tangent? Opposite over adjacent, is that what I heard? No. Tangent is opposite over adjacent. Okay, and that's Roman numeral 6. Cosecant is, it's what? No, that is cosine, is adjacent over hypotenuse. The cosecant and secant always have hypotenuse on top, because those are greater than 1, or sometimes equal to 1. So cosecant is hypotenuse over object, opposite, Roman numeral 3. Okay? Secant would be opposite over adjacent. Is that what you said? No? Oh, yeah, I'm sorry. Secant would be hypotenuse over adjacent. That's exactly right. And that would be Roman numeral 1. And cotangent would be adjacent over opposite, which is Roman numeral 2. Very good. Number 2. Relative to the acute angle theta, the three sides of the right triangle are the blank side, and the blank. We've just been using all three of those words. Okay. Usually with hypotenuse you don't use the side, so that would be the third one, and the hypotenuse. So what would be the first two? Opposite side and the adjacent side. Perfect. Number 3, cofunctions of blank angles are equal. Oh, your hair's pretty today. I was giving you a complementary angle. So the cofunctions of complementary angles are equal. CO, complementary. Okay. Number 4, an angle of blank represents the angle from the horizon upward to an object, whereas the angle of blank represents the angle from the horizontal downward to the object. Which is which? Elevation is the first one. Depression is the second. Good. Homework exercises here include any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. 11 and 13 are both at Calc Chat. Any of the odds 15 to 21, they're all at Calc Chat. Any of the odds 27, they're all at Calc Chat. 27's at Calc View. Any of the odds 29 to 35, they're all at Calc Chat. 37 through 41 are all at Calc Chat. 39's at Calc View. 43 through 51 are all at Calc Chat. 47's at Calc View. 53 to 57 are all at Calc Chat. 59 or 61 are both at Calc Chat. And then applied problems 63 through, 73 should all be at Calc Chat. Okay? There's a Few true false, 75 through 79 are true false. They should be at Calc Chat. You can think about doing 81 if you'd like, and or 83, and they should be at Calc Chat as well. All right, any question on those? Okay, so let's proceed to, if there's no question, we'll go to 4.4. For some reason my head is clogging up like crazy. All right, go to 4.4. And we've got 16 minutes, right? Okay. See how far we can get. All right. We'll go from current slide, which is the beginning also. Still in Chapter 4, trigonometry, but 4.4 is trigonometric functions at any angle. Now, there are a few ways you could do this. The book focuses on one. Frankly, it's fine. I use it all the time too, but there is another way you can do it that works out just as well, and I'll try to show you both methods. Okay, but we, on unit circle, we deal with the unit circle because it's all covers all four quadrants. So far, in 4.3, we only dealt with acute angles in the first quadrant. Okay, they live. 4.3. So now we're going to expand our right triangle trig to go to any angle, any quadrant, any direction. We're going to use that. Okay? So we'll evaluate trigonometric functions of any angle. That's the whole purpose of this section. We'll find reference angles. Frankly, we'll find reference angles in order to do that. So this one I think should have come first. And we'll evaluate trigonometric functions of real numbers, which is what we've been doing too, especially with unit circle. All right, the introduction here, and if you haven't gathered yet, this is pretty important. It looks a lot like what we've done before, however, there are some slight differences. Definition of the trig functions were restricted to acute angles in the last section. In this section, well, definitions are extended to cover any angle. So if theta is an acute angle, meaning you're in the first quadrant, the definitions here coincide with those given in the preceding section. But if you're in any quadrant, these still work. Okay? Now, we're going to let theta be an angle in standard position, meaning measured from the positive x-axis counterclockwise around to the point xy. In the previous section, xy was always in the first quadrant. Now it's not going to be. Okay? So this x they show here happens to be a negative number. The y still is a positive number. If you were down here, x would be negative and y would be negative. If you were over here, x would be positive and y would be negative. But you still use the xy. Okay? So we're going to let theta be an angle in standard position measured from the positive x-axis around one direction or another to any point xy on the terminal side of the angle theta. Now, I'm showing it here in the second one. Here's something I know you know about, we haven't necessarily done though. If you know that xy, whether x is positive or negative, whether y is positive or negative, you know what r is. R is the square root of that vertical plane. Okay? Now, notice there's no sign in front of that. It's not plus or minus. It's plus the positive square root of that. If x is positive or negative, when you square it, it's going to be positive. If y is positive or negative, when you square it, it's going to be positive. So this is going to be a positive number. You're adding a positive number to a positive number. That gives you a positive number. Square root of a positive number, the positive square root. R is never zero and it's never negative. R is always positive and never zero. Now, the only way it could be zero if you were at the origin. Okay. Well, you don't have any angle if you're at the origin. You're just there. Okay. So that's why we say R is never zero and it's always positive. Now, hopefully these look similar. If you were in the first quadrant, Y was your opposite side, R was your hypotenuse, right? So this is sine is opposite over hypotenuse, Y over R. Cosine is adjacent over hypotenuse, X over R. Adjacent side is your X. Tangent is Y over X, opposite over adjacent. This is as long as X is not zero, so you exclude the half pi, or the 90 degrees, okay? Cotangent is Y over X. Now Y can't be negative, so you exclude your whole pi, or zeros and 1/8 multiples of those. Okay, secant is R over Y. No, so R over X, which is reciprocal of cosine. Again, X can't be zero, just like you can't here. Cosecant is reciprocal of sine, R over Y. Of course, Y can't be zero. Same thing we had before, except we call it opposite and adjacent. Or, even on the unit circle, R was always 1, remember? On the unit circle, X squared plus Y squared was always 1. So in the unit circle, this is just Y, X, Y over X, X over Y, 1 over X, and 1 over Y. Okay? Everything fits. Okay? Now, because that R is the square root of X squared plus Y squared, it can't be zero. It follows that the sine and the cosine functions are defined for any real value of theta. Why? Because your R is your denominator. It can't be zero, so therefore these are defined everywhere. The other four have restrictions. There are places they can't be defined. Okay? However, when X equals 0, both tangent and secant, none defined, because you can't divide by 0, and they are, tangent is Y over X, X can't be 0, and secant is R over X, X can't be 0. So, for example, the tangent of 90 is undefined, because at 90 degrees, your X value is 0. Similarly, when Y is 0, cotangent and cosecant are undefined, because cotangent is X over Y, cosecant is R over Y. Both of those undefined when Y is 0. All right, let's do example 1. Let's let -3, 4 be a point on the terminal side of theta. Where are we, Waldo, when you're at -3, 4? Say again? Third, you said? Y is still positive. Okay. Say again? Okay, not third. Not in the fourth. Your X is negative. Second, because your Y is still positive. Okay? All right. Waldo doesn't know where he is. Okay, no, okay. Now, let -3, 4 be a point on the terminal side of theta. Find the sine, the cosine, and the tangent of theta. So let me get my pen set up. Okay? What is the sine of theta? In terms of X, Y, and R, which is not yet determined. What is the sine of theta? It's what? Okay, okay. Not quite. Say again? Y over R. Okay? And we know Y, that's 4. Do we know R? Say again? We may not know it right now, but we sure can figure it. It's what? Okay, it's the square root of, what do you say? X squared plus y squared. And your x is negative 3 squared plus your y is 4 squared. So that would be the square root of, what's negative 3 squared? Okay, the total is 25. Okay, 9 plus 16 is 25. And what's the square root of 25? 5. So this will be 4 over 5. Sine theta is 4/5, or you could write it as 0.8. Doesn't matter which way you write it. Just using the point. The point, use it to calculate r, and then use the values to give you sine. Okay, let's do cosine. What would it be? X over r. And what's your x? Negative 3 over what? 5. And that is negative 3/5, or negative 0.6. Very good. What's your tangent of theta? Y over x, which is negative 4 over 3. Is that what you said? Okay. Now, let's see if at least your signs, SIGN signs, make sense. Okay? You told me this was in which quadrant? Second quadrant. What's true about the second quadrant? Hey, that's true. But about your trig functions. I know that in the first quadrant, all the trig functions are positive. How about the second quadrant? Okay, so what trig functions are positive here? Second, anything with positive y, with a y. Which trig functions have y's in them? Sine. Okay, because it's sine, y over hypotenuse. Hypotenuse is always positive. That's it. All students take calculus. Sine and its reciprocal, which is not cosine. Reciprocal is sine is secant. Cosecant. Okay. So all are positive here. Sine and cosecant only here. And sure enough, sine is positive, wasn't it? Okay. And everything else is negative, including cosine and tangent. Both negative. Down here, what's positive? Tangent. All students take tangent is positive, and its reciprocal, which is cotangent. So those are positive here. We're not down there with this problem. Forget that. But over here, what's positive? All students take calculus. What starts with C? Cosine. Yeah. Of course, cosecant, cotangent too, but we've already taken care of that. So cosine is positive here, and its reciprocal, which is what? C. Its reciprocal is C. So, all right. So this, at least by the SIGN sign, that's what? Positive, negative, and negative. Okay. I think that's all we had to do with that one. So let me, can I erase? Yay or nay? Okay. Let's see how they do it. Referring to the figure, you didn't have to draw it, but they did. Negative 3 for x, up 4 for y. And they drew what r was, but it didn't tell you. But here they tell you r is the square root of x squared plus y squared, which is the square root of negative 3 squared plus 4 squared, which is square root of 25, which is 5. Okay? Once you have that, you can write down what the sine, you can write down all 6 of the trig functions. Sine is y over r, 4 over 5. Cosine is x over r, which was negative 3 over 5. and tangent is 4 over y over x, which is 4 over negative 3, which is negative 4/3. Okay? Make sense? Just pretty much a piece of cake. Okay? Now, they're skipping examples. No, they're not. This is what's next. And this is what I was just telling you. Sorry, jump the gun. The signs of the trigonometric functions in the fourth quadrant can be determined from the definition of the function. For instance, because cosine of theta is x over r, anytime r is always positive. Okay? So anytime x is negative, cosine is negative. X is negative, second and third quadrants. X is positive, first and fourth quadrant. So cosine is positive, everything's positive in the first quadrant, and it's also positive in the fourth quadrant. Okay? Follows cosine is positive whenever x is greater than 0, which is in quadrants 1 and 4. Remember, r is always positive. Never 0, never negative. Okay. Let's see if they do example 2. Oh, here it is. In a similar manner, you can verify the results shown here. So, in the first quadrant, that's anytime theta is between 0 and pi halves, the x's are positive, y is positive, everything's positive, okay? In the second quadrant, your x is negative, y is positive, so only sine, which depends on y, and its reciprocal, which is cosecant, are positive here. The other 4 are negative. Down here, x is negative, y is negative, so but of course your hypotenuse is always positive, so your sine and your cosine and their reciprocals are all negative because x's and y's are negative. But because negative over negative is positive, that means your tangent and cotangent are both positive here. And by the way, this is pi halves to pi. This is pi to 3 halves pi, and this is 3 halves pi to 2 pi. Getting say that 0 to 90, 90 to 180, 180 to 270, and 270 to 360. Just to get that out of the way. Over here, fourth quadrant, x is positive, y is negative. So sine is negative, tangent's negative, the reciprocals are negative, the cosine is positive because that's x over r, and its reciprocal r over x is c. Positive. So again, all are positive here. We only listed the big 3. You know the reciprocals. Okay, they'll be the same. All sine, tangent, cosine are positive. All students take calculus. All state technical college. Any way you want to put it together. All students take chemistry. Whatever you want to remember that by, those are the positives. Everything positive in the first, sine, cosecant in the first, in the second quadrant, tangent, cotangent in the third, and cosine and secant in the fourth. Now, they're skipping examples 2 and 3. How are we doing on time?
It's 11:17.
It's what, 11:13? Just 2 minutes left? Is that right?
11:17.
Oh, 11:17. Oh, you've run over again, haven't you? Okay. But guess what? I'm not going to charge you any extra. Okay. So we'll pick up example 2 next time. Let me give you the homework exercises in 4.4. They will be any of the odds, 9 through 11, or 9 or 11. They're both at Calc Chat. 11's at Calc View. 13 through 17, they're all at Calc Chat. 19 or 21, they're both at Calc Chat. We'll pick up the rest of those next time. Okay. Now, also, I'm going to try to, next time, whether we finish 4.4 or not, I'll try to have your test ready. First test, because first test comes after 4.4. It's going to be close enough that you can get started on it. Even if we don't finish by Thursday, we'll finish, and you can go from there. Good deal. Any questions? All right. Give you something to look forward to.